All right, in this video lecture 15, we're going to talk about using the idea of statistical significance to answer this question. If we see a difference between samples, do those differences reflect true differences between the populations of interest, or do they just reflect random variation between our samples that could happen by chance? So Statistics Without Tears talks about two methods of doing this to determine whether your data gathered on two samples can be interpreted to mean that there's a real difference between the samples and therefore the populations. So for example, in a medication study, if we have data from our placebo group and our active medication group and the two sample distributions show different means, can we be sure this difference isn't just due to random chance, right? Does a difference between the means of those two samples reflect a real difference between the populations represented by the samples, or a real difference between samples from the same population subjected to different treatments? And you saw in the book, Roundtree uses the difference between male and female blood pressure readings to look at this, and his diagram on page 106 of the book I think is really helpful. So you saw the two methods that he talks about. The first one is calculating the overlap between two distributions of sample means, and that's the concept talked about on pages 104 to 107. But then he goes on pages 107 to 118 to talk about using the distribution of differences between the means of pairs of samples to calculate the standard error of the difference between the two groups. Okay, so hopefully you've just read this before watching this lecture. If not, and you were unclear on any of that material on pages 104 to 118, you should probably stop the lecture and review that right now before going on. Okay, so the first method Roundtree talks about on pages 104 to 107 involves figuring out, well, what are the chances that the two distribution of means of our samples would overlap, right? And this involves looking at the actual overlap of the normal curves that you get when you do the standard error of the mean distributions, right? So what he does is to figure out the standard error of the mean of both samples to get that estimate of the range of possible population means, right? And we know that the sample mean distributions are always going to be narrower than the sample distributions themselves, right? As he shows on page 106, and as I've tried to show here on the slide with my hand-drawn little blue curves. So looking at this slide, right, the black curves here are our two samples. You can see there's quite a bit of overlap, right? But the blue curves here, much tighter curves, right, represent our sample mean distributions. So if you look at the overlap here, right, the overlap of the sample mean distributions, obviously much smaller than this larger overlap we had with just our two samples. So Roundtree does this in the book, and he then calculates the probability of picking out a random pair of samples that in fact would fall into this small area of overlap. And in the book, he uses the 99% confidence interval, right, which translates into a p-value of 0.01. And you saw he determined for his example that in fact only 1 out of 100 samples would the female mean blood pressure fall outside that 99% range of 106 to 114. So yeah, and then in only 1 out of 100 male samples would the mean fall outside the range of 116 to 124. Okay, so again, the female blood pressure means, right, were lower than the male means. And it was really only 1 out of 100 that the mean would fall outside of the range of 106 to 114 in females, or 116 to 124 in males, okay? So you've got two 1 out of 100 probabilities. So to figure out the probability of both of those things happening, right? If all you're doing is taking one sample of females and one sample of males, right? And what are the chances of their means falling outside that 99% confidence interval range? Both of them. You can use the product rule to do that, as he did. So you just multiply those two probabilities. So 1 out of 100 times 1 out of 100 is 1 out of 10,000, right? But then he points out that within that 1 out of 10,000 chances, there are actually 4 possibilities. So looking at our curve, the 4 possibilities are both your female means and your male means might be low, right? Well, we're not interested in that because there's no overlap there, right? Or both the female means and the male means could be high. Not interested in that either because there's no overlap. Or the female means could be low and the male mean could be high outside of that 1%. We're not interested in that either because there's no overlap. This is the only area we're interested in where the 1 out of 100 chance happens to fall in your female sample on the high end, and the 1 out of 100 chance in the male sample falls on the low end. That's where you get your overlap. And that only happens in 1 out of 4 possible scenarios. So we use the product rule again, take 1 out of 10,000 times 1 out of 4, right? Since we're only interested in the probability of that 1 out of the 4 combinations. And there we see that the chances of 2 random samples falling into this overlap here are only 1 in 40,000, or 0.000025. So you saw in the book, Roundtree then declares that the chances of this overlap are negligible, and so one can be almost certain that the female blood pressure readings were drawn from a different population than male blood pressures, right? Okay, but as Roundtree then goes on to say, this is not, in fact, a commonly used method, and instead, this is usually done mathematically. I would say nearly always done mathematically, right? And you do that by calculating what is called the standard error of the difference. And that's just the difference between the means of an imaginary infinite number of pairs of samples. You don't really take an infinite number of samples, right? You only take one, but you calculate the difference between the means of an imaginary infinite number of pairs of samples, okay? So you're thinking in terms of the distribution of differences between the means of samples. Okay, so the idea here, and again, if you didn't understand this, I strongly suggest you reread those pages in the book. But the idea here is that if you were to draw an infinite number of sets of 2 samples from a population, and you always subtract the mean of sample B from sample A, okay, and if you then go and plot the differences in means, you end up with a frequency distribution that is going to be normal. It's always going to be normal, no matter what the distribution of your samples really were, right? And the mean of this distribution of differences is going to be 0, right? A mean of 0 differences between sample A and sample B. And the fact that this is a normal distribution is, of course, lucky for us, right? Because that means that all those same proportional calculations can be assumed. In other words, if 68% of the differences between sample means, right, 68% of those differences are going to lie somewhere between -1 and +1 standard error of the difference, right? And 95% of the distribution of differences is going to fall between -2 and +2 standard error of the difference, and so on, right? And we know that this 95% confidence interval idea corresponds to a 0.05 level of statistical significance, this 95% level right here. So if we go back to compare our original two samples, right, and we calculate the standard error of the difference mathematically, right, instead of having to take an actual infinite number of samples. If we do that calculation and the result falls outside, right, outside this 2 standard error range, we can then say that we are confident that there is a real difference between the two populations from which our samples were drawn to the 0.05 level of statistical significance, or even the 0.01 level if we get to outside this 2.5 standard error range. Okay, so this is the mathematical formula for standard error of the difference between two samples, which you can see, right, involves first calculating the standard error of the mean, right, of each sample, sample 1, sample 2, right? And then, which by the way, that formula is up here on the slide, right? We calculate standard error of the mean by using the sample standard deviation, right, divided by the square root of the sample size. So those values go in here and get squared. They get squared, added together, and then you take the square root of that, and that's how you get your standard error of the difference. Okay, so we're going to do this example together. I'd like you to get a piece of paper and a calculator if you need it, and you know, pause in these slides to actually do the math yourself. I think it would be helpful, but you're on the honor system there. So here's our example. There's a medical researcher who wants to study the efficacy of a new weight loss pill, okay? So she takes a treatment group of 100 people. She has a control group of 400 people. Treatment group of 100 people, control group of 400, okay? And let's assume that there's a placebo pill for the control group and the actual weight loss pill for the treatment group of 100. And in the treatment group, the mean weight loss over 3 months of the study period was 1.2 pounds. In the control group, it was 0.2 pounds, right? So the difference between the means of our samples is 1 pound, okay? And I'm telling you the standard deviation, both groups have a standard deviation of 4 pounds. So we're going to do some calculations. First, if we want to figure out the standard error of the difference to see if we can declare there's a statistically significant difference here between these two groups, we have to start with this formula, and that means we have to calculate the standard error of the mean of each of our groups. So let's start with our treatment group of 100 people, right? What is the standard error of the mean of the treatment group? Okay, and again, that formula is here. I encourage you to pause the video while you figure that out. Okay, so plugging those numbers in, standard error of the mean of the treatment group, right? So again, standard deviation is 4. You divide that by the square root of the sample size, right? Square root of 100 is easy, that's just 10. So 4 over 10 is 0.4, standard error of the mean of the treatment group is 0.4. Okay, but we've got that number we can plug in here, but now we need the standard error of the mean of the control group. So go ahead and do that math as well. Okay, so the math here, again, pretty easy. Our standard deviation of 4 divided by the square root of 400, which conveniently is 20, gives us 0.2 for our standard error of the mean of the control group. Now you have everything you need to calculate the standard error of the difference. So go ahead and do that. Okay, so here's our formula for standard error of the difference, right? First, we have to take our standard error of the mean for the treatment group, square that, and we have to add the standard error of the mean of the control group that has also been squared, and put our numbers in there. We do that math. We end up with the square root of 0.16 plus 0.04, and the total here, 0.16 plus 0.04 is 0.2, and the square root of 0.2 is approximately 0.45. 0.45 is our standard error of the difference for those two groups. Okay. Now, here's the important question. You're the researcher. Is there a statistically significant difference between these two groups at the 0.05 level? So pause here and see if you can answer that question. Okay, there's a couple ways you could go about calculating that, but we know that the difference between our sample means, right, was 1 pound, and the standard error of the difference is 0.45. And to get to the 0.05 level of statistical significance, we have to be more than 2 standard error of the differences out, right? And in fact, our actual weight loss of 1 pound is more than 2 times the standard error of the difference, right? In fact, we got all the way out to 2.2 standard error of the difference. So yes, we have reached the 0.05 level of statistical significance. How about this question? Is there a statistically significant difference at the 0.01 level? So here, to get to the 0.01 level, remember, we have to be at a difference of greater than 2.5 standard error of the difference, okay? But we already know from our prior calculation, our difference of 1 pound is only 2.2 the standard error of the difference here. And so, no, we didn't get to the 0.01 level of statistical significance here. Okay, so in the book, Roundtree on pages 128 to 133 talks about the two-tailed test versus one-tailed tests. He's using his example of the memory pill, right? And you saw in that example, if a researcher has an expectation about the direction of the difference that's going to be seen between the two groups, or usually more specifically, you know, when the alternative hypothesis that you're attempting to falsify only involves one side of the normal curve, a researcher will sometimes use the one-tailed test. So this is a classic situation where you're testing a pill like the memory drug in the book or like the weight loss medication in my example we just did. So basically a one-tailed test that compares two samples involves the researcher putting all of the differences between samples on one side of the normal curve. Okay, so for example, here we see a typical two-tailed test curve looking for significance at the 0.05 level. So you know what we do is we take that 0.05, right, and we split it, right? So we actually get 0.025 at each of the far ends of our normal curve. And we know this is going to be basically 2 standard errors out from our mean. But if we think we know the direction of the difference, like in our pill versus placebo pill example, we only want to reject the null hypothesis of no difference if the pill group shows a significant difference at the 0.05 level of improving our outcome, right? Like more weight loss or better memory results. So we might decide to do a one-tailed test and basically put all of our eggs in one basket, so to speak, put all of our 0.05 out here on one end. And this, as you saw in the book, basically allows the researcher to reject the null hypothesis if the difference is only 1 2/3 about standard errors out from the mean. So some people do criticize the use of the one-tailed test for that reason, because researchers are making it easier to reach the 0.05 level of statistical significance. And here is the same comparison at the 0.01 level, right? Normally, if you have it divided on your normal curve, right, you have to be out 2.5 standard errors of the differences to declare statistical significance at the 0.01 level. But here, if you do a one-tailed test, you can declare that you've attained 0.01 if you only have about 2 1/3 if you're beyond 2 1/3 standard error. And Roundtree shows this in the book on page 132. So I don't know if you remember the data that we got, but going back to our weight loss drug example, if we used a 0.01 significance level, and remember we didn't reach when we were doing the two-tailed test. The question is, how about if we used a one-tailed test? And remember, with the one-tailed test, you have to be out about 2 1/3 standard error of the difference. And remember here, we didn't quite get that, right? We were only out 2.2 standard error of the difference. So even with a one-tailed test, we're not going to make it here. And then the last thing I want to talk about here is I think this weight loss drug example is a great example of the difference between statistical significance and practical significance, right? Is a 1 pound difference in weight loss over 3 months practically significant enough? Should this pill get marketed? I would say it probably depends on the side effects. But we also might want to look more carefully at our data, right? If a few people did a lot better on the pill, you know, we probably want to analyze them in particular to see if there's something special about those people that seem to react the most strongly to the medication, to consider maybe marketing it to a specific subset of the population. Okay, this is the end of video lecture 15.